I know I set to Rodolfo a talk on in situ absorption, and mainly the talk concerns about in situ, but also I have this talk prepared beforehand to also give some generalities on sound absorption, which maybe is interesting for the audience. So I'll try to cover that part faster and then get to the in situ and cover it in more depth. I'm speaking in English because I'm sorry, I don't speak Spanish, and I'm not gonna try to butcher the Spanish language by doing the mix of Portuguese and Spanish. So I'll go in English, but if you have any questions, you can ask in Spanish, and if you speak slowly enough, I think I can understand. For this talk today, I'll talk a little bit about our end of the world here in the university and the acoustic engineering program we have. It's mainly based on the acoustic engineering in Austral University in Chile. I'll talk a little about sound absorption generalities and a bit on the standardized methods, the reverberant room and impedance tube, and then I'll dive into the in situ methods, giving some historical perspective and recent projects with using microphone arrays or arrays of receivers. Where we're here in the south of Brazil. Brazil is a very large country. I was born in the south of Minas Gerais. It's about 1,500 kilometers from here to where I live now. We're really in the middle of the last state of Brazil in the south. So below us is Uruguay, and to the left, Argentina. And I like to give a comparison to the place I'm talking to, and to actually, instead of making sense of gross numbers like area and population, I like to, as we are talking to acousticians, I like to give a comparison in decibels, which I think it's nicer. So Brazil is about 20 decibels larger than Chile. The population is also about 20 decibels larger than Chile. Our GDP per capita in terms of ranking is lower, about 7.5 decibels. And I am sure that sooner or later in acoustics, we will get to a comparison of numbers that results in not a number. So inequality index in Brazil is still high. Unfortunately, in Chile, it's a median according to the last data that I could look into. So we are at this federal university, which means we are owned by the government and paid by the government, the federal government in Brazil. We are about 26,000 students so far. And we have combining undergrad and postgrad courses, 260 courses. We're about 2,000 professors in all career levels. And we are in the top 2.5% universities in Brazil, according to later rankings that come out this year. Here we have the first and only acoustical engineering undergrad program in Brazil. You have one very similar in University of Austral, and in fact, our curriculum is based on your curriculum. And about 25% of our former students are working abroad. Europe and the US have been accepting quite well our students. And in Brazil, most of the people that came out of the course are working in building construction because of some new standardization that came in 2010 on that forces buildings to comply to a certain level of sound insulation. So as I said, we have a very similar curriculum, and I teach here room acoustics, bit of electroacoustics, introductory electroacoustics, and I also teach signals and systems and digital signal processing. And of course, I advise our bachelor thesis and internships. And the bachelor thesis here takes 2 to 3 semesters. It's a long process, and there's a process where the students are actually have to face real research and dive into that level of work. We are 5 to 7 professors. There are still open spots, and we are dedicated to this last half of the course, of course, other course activities as well. And we are different from Europe. We are a 5-year engineering program. So it takes 5 years to do engineering in Brazil. I'm not sure how it goes in Chile, but that's about it around here. And part of the job here, due to also show social inequalities, that people come from all sorts of backgrounds, and many times students of us wouldn't have access to speaking English quite well. So we try to actually write also literature, and I had the chance to write this book in room acoustics. It's a very long book. It's in Portuguese. I'm sure you can maybe try to read it if you're interested too. And if you're interested, you can write to me or just Google for the title here, and you'll see a link to the book. Got a prize in Brazil, so it's a work we're proud of around here. Okay, so diving into the topic of today, I'd like to give a quick overview of sound absorption and generalities and why it's important and so on. Okay, so we have basically 2 types of sound absorbers. Porous absorbers. In porous absorbers, we have sound propagating in the bulk of material. We have rock wool here and foam on the left. And these materials contains tiny pores, tiny spaces through which the sound will propagate. And losses are caused by viscosity, thermal conduction, and skeletal vibration. Usually we model this kind of material with the physics of an equivalent fluid, which means that we specify sound speed and fluid density that becomes complex and frequency dependent. And with that values, we can actually calculate the sound absorption of the material. This is just a basic idea. And on the other hand, we have resonant absorbers that are commonly used in small rooms and large rooms as well. Basically, the absorption characteristics in that case is due to a mass vibrating over a spring, and the mass can be, in the case of membrane absorbers, the membrane itself, and the spring is the air contained inside the cavity. And we have like perforated plates that are commonly used as well. The spring is also the air locked in the cavity, and the mass is the air plug in the perforations or slits and so on. In that case, we have a multi-layered system. It's common to fill the cavity partially, at least, with porous material to increase the absorption characteristics of such materials. Absorbers are everywhere. We find them not only in room acoustics. We, of course, use them at large in room acoustics to treat the characteristics of the room, but also we use them in aircraft, for instance, lining the engine of the aircraft to reduce the noise emission. We use them can use them in roads as well, when we have a porous asphalt, for instance. It will absorb sound a little bit and also contribute to water flow and so on. And so sound absorbers are used in many applications for noise and reverberation control and the characterization absorbers is important for better design and quality control of our applications and machines, and also rooms, as Ritka was saying in his previous talk and questions. We have some standardized and non-standardized measurement methods that I will try to cover today. And we have those in situ techniques. That means that we take the measurement apparatus to the sample instead of taking the sample to the lab. And those in situ methods, they can provide information and applications inside. So, okay, I'm sorry, I think I unshared in a way. So, okay, so sound absorption, it's a little of definition we have of quantities. Usually we measure the sound field above an absorber and compute the absorption characteristics of the material. So we don't have access to the inside of the material or to the surface of the material. So we have to measure somewhere outside the material many times. And we have those quantities that are the absorption coefficient. It's defined between the ratio of absorbed power over incident power, and it goes from 0 to 1. It is a real quantity. We have the reflection coefficient, which is a certain counterpart of the absorption, which is the reflected amplitude of the wave and the incident. And this can be a complex quantity. And the modulus of the reflection coefficient varies from 0 to 1. And it's related to the absorption through this formula here. And then we have the surface impedance, which is a measure of the ratio between the pressure and the normal component of the particle velocity on the surface of the material. So it is defined exactly on the surface of the material. It's complex and frequency dependent. But the thing is, it's defined on the surface of the material, and frequently we don't have access to the surface of material to measure this quantity. In terms of general behavior, porous materials do tend to have an absorption that increases in frequency, and in resonant absorbers we would have resonance, and then below the resonance the absorption is sort of small, and after the resonance as well. So what I mean when I said that we don't have access to the surface is the main framework in which every method to measure absorption works. Typically, we have a sound field that is created by a sound source, and we have a receiver that we measure. This can be, this scenario can be anything. This scenario is very general, so keep in mind that. And what usually happens is that we rarely measure things directly in acoustics. So we don't have a machine that actually kind of measures the absorption. So we have methods in which we can measure the sound pressure or particle velocity in a point above the material. And then we use a model to compute the absorption or impedance or reflection coefficient. So this process happens every time. What can we say about the model? Well, we have scenarios in which we assume diffuse field, or scenarios in which we assume that we have one plane wave or spherical wave, or we can make assumptions about the sample, for instance, that the sample is large enough or infinite, or the sample is locally reactive or not, and so on. So I like you to have this picture in mind, so that we measure pressure with a microphone, which is more common, or particle velocity, and use a model to retrieve the sound absorption. So what can I say about the standardized methods? So the reverberant room methods is based on the ISO 354. It is to measure the sound field in a reverberant chamber. Typically, we measure in two conditions, with and without the material. It assumes that we have a perfectly diffuse sound field, meaning that the energy density is uniformly distributed in space. That means also that the energy flow is dropping in the room, and if that's the case, then we can use Sabine equation to actually measuring the reverberation time, then we can compute the absorption. So usually it's measured in a large reverberation room. We excite the room with a broadband signal, and the microphones capture the decay or the impulse response in this sound field, and we measure with the sample here or without the sample, compare the two situations, and retrieve the absorption of the sample. So what is measured really is what we call the random incidence sound absorption coefficient, which can be seen as an average over all angles of incidence. So we don't have the absorption per angle of incidence, but we have the absorption as an average of all angles of incidence. It is a widely known method. There are extensive databases to use, for instance, in room acoustic simulations and so on. And of course, this is standardized. So what I mean by measuring two conditions is this, that without the material, the decay will be longer, and when we put the material, the decay will be shorter, and then comparing the two situations, we have the absorption, which is standardized and easy to retrieve mathematically. So that's it about the reverberation room. The drawbacks is that only this mean quantity over all angles of incidence is measured, not the impedance. A reverberation room is required, which can be quite costly. You need large samples required for 10 or to 12 square meters of samples, and it is well known and reported in the literature that sometimes the absorption that is computed in this method can go above 1, which is not physically possible, but it is what we retrieve, and that has been attributed many times to the edge diffraction effect. And another thing that is important is that the diffuse field assumption that is important in this method is not completely fulfilled, and there's been evidence reported recently in the literature that the sound field is non-isotropic in many rooms, especially when we put the material inside. And also, it has been reported recently high interlab uncertainty, so measuring the same sample in many labs returns different results. So the other standardized and well-known method we have is the impedance tube. In that case, the model of the sound field is a plane wave at 0 degree incidence or normal incidence. So we have one incidence and one reflected plane wave inside our tube. And with that assumption, we can compute the pressures at those microphones and then retrieve the absorption coefficient or end surface impedance under normal incidence. So in the impedance tube, the sound source excites the tube, and then with broadband signal, and then the sample is on the other side. And instead of measuring only solely the pressure on those two microphones, we usually measure the transfer function between those signals, and then we can compute the absorption. Here, we can measure sound absorption, reflection coefficient, and surface impedance, but under normal incidence and plane wave incidence. So only the 0 degree incidence is recovered. It is also widely used. It is somewhat portable because you can build this tube to fit a small dinner table, for instance. You can build larger tubes as well, but you can build small ones and have good results in a dinner table, if you like. So you don't need a very large reverberant tube. The drawbacks is that the quantities measured are measured only under normal incidence, 0 degree incidence. It is a destructive method, so we have to cut the sample to actually be able to measure. There's been also evidence of high interlab uncertainty reported in the past. And we also find out in a project we had with the Embraer, that is the Brazilian aircraft company, that only cutting the samples and mounting them in the tube already represents some uncertainty in the measurement. So what we did was, one of the things we did in this project was to get a sample of the material that we cut very carefully, and then we mount the sample in the tube, measure, then we take it out, mount it again, measure. So the same sample was mounted and dismounted many times, and we do not measure exactly the same curve of absorption, but we have a deviation in frequency. So maybe measuring only one sample is not wise enough. So you need to measure like 10, 30, 50 samples in the impedance tube. And of course, it's hard to measure samples with surface variations, such as membrane absorption, large metamaterials, and so on. And if the material has an undulated surface, you have to arbitrarily define where the surface of the material is, because this distance from the microphones is important in the calculations. All right. Now I can finally talk a bit about in situ methods. Try to keep track of the time as well. So I'll give some perspective and talk about microphone arrays, and that will be mostly of it. So what is if with the in situ methods? So the term in situ means is a Latin word for on site. So that means that we are taking the measurement set up to the sample. That's what this picture of me is saying. So we took this method, this experimental apparatus to the inside of a car, for instance, to measure the absorption of the ceiling of the car. I worked for a couple of months at Microflowne Technologies when I was starting my PhD. This was to get acquainted with the technology and so on. So that's when they took this picture, which they seem to like and use it many times. So the in situ, you have many methods. And I managed to publish a review paper in 2015, reviewing many of those in situ methods that I knew of at the time. And I think, as far as I know, there's been little activity. The only field that evolved quite a lot in recent years was using arrays of microphones to measure. So this review doesn't cover that, but it covers many methods available until 2015. And some of those methods, we can have freedom regarding the angle of incidence. So that means you can measure the absorption as a function of the angle of incidence and frequency. And over the historical perspective of the development of such methods, one can see a trend of increasing mathematical and procedural complexity since the 50s, the 1950s, when they started to propose in situ methods. So we can see that it evolved from plane waves to spherical waves and iterative methods, and now we have the array methods that is seem to be more procedural complex. So how can we do in situ? So we have some approaches that we can take. I'll cover some of them today. So the first one that I think it's very intuitive is to use time separation methods. This was proposed in the late 1990s by Gray and Momets. And the idea is that we have a loudspeaker in a room, and we have the material you want to characterize, and you have a microphone. Then you can measure the impulse response of this configuration, and the impulse response of this configuration will have three key components. The first is the incident sound field that the loudspeaker forces in the microphone. The second is the reflected sound field from the sample in the microphone. And the third is the spurious reflections in the room. And if we measure, imagine that now this room is an anechoic room, there's no material, and then you can measure in free field conditions just this first component. So no spurious reflections and no reflections from the sun. So if we have the second measurement with the incident sound field, we can use a subtraction method. So we can subtract this scenario that is in situ from the free field scenario, and then you remove the incident sound field, and then you end up with the reflected sound field from the sample, and then you can window this to exclude the spurious reflections, and then you have a separation of the reflected and the incident, and then you can compute the reflection coefficient. So this is very intuitive in a sense. It involves a lot of signal processing, but it is intuitive. There are some available corrections for spherical wave incidence. It is possible to include it, but it's limited in some senses. And we have some difficulties measuring the low frequency range, because typically in the low frequency range, the impulse response of the incident sound field would mix together with the reflected and the spurious reflection. So there's no sensible way to separate them. Another way to do it, and that is increasing in complexity now, we can perform measurements with a pair of microphones or with a pressure and velocity probe near the material. And in that case, the model that we have is a sound field and the reflection. And we can compute the transfer function between microphones or the transfer function between pressure and particle velocity. And we can assume something about the sound field. For instance, in the past, Allard proposed the methods assuming plane waves impinging in the material, in the microphones. Later on, we moved on because this assumption is not very good at the low frequency range. Then we moved on to assume spherical waves on specular reflection. This was proposed by Ian Hodgson in the late 1990s. And this assumption is also not so good in the very low frequency end. It's a bit better than the previous, but not so good. And then we come up with full reflection models. That means that if you move your source close to the sample or the microphones, the wave field is not plane anymore, or the spherical waves do not reflect on specular reflection, but the reflection, the spherical waves do tend to diffract in the material surface. And that creates a model that is very complicated to evaluate. It has this difficulty integral here with the reflection coefficient of the sample. This is a Sommerfeld integral. And then when you use this full reflection model, the advantage is that you can use more portable devices, such as the one that microphone technologies proposes to use, which is the loudspeaker is about 30 centimeters on the sample. but you sort of need this full reflection models, and this full reflection models, you cannot retrieve the surface impedance easily with the inversion of an equation such as the impedance tube, but you have to use an iterative method to retrieve the surface impedance. So also the drawbacks is that the sound field model that you use here, even if with a full reflection of the spherical wave, you may have some restrictive assumptions, such as assuming that the sample is locally reactive or assume that the sample is infinite. And those assumptions can lead to some deviation from true results. So typically, if you're measuring a finite sample and assume that the sample is infinite, then you have this typical oscillations that we found numerically and experimentally. And if you assume that the sample is locally reactive and the sample is not, then typically you kind of overestimate the absorption coefficient, which we also observe in the model and experiment. We also have been using around here a method that is very practical. It was proposed by Takahashi, Otsuru, and Tomiko in Applied Acoustics in 2005. Here, the idea is that you use a pair of microphones near the sample, and you are sort of in a room, and you can excite the room with a loudspeaker, or you can just use the ambient noise present in a restaurant, for instance, or cafeteria. And of course, the microphone and sample will be excited through all angles of incidence at the same time. And then we can use a simple model to retrieve surface impedance. It is a simple method, and you can get good insight on the characteristics of the material. Different from the reverberant room methods that is standardized. Here, you measure close to the sample, and you are under some kind of diffuse fields. But the tricky part is that the model that has been proposed in this original paper, it's a bit contradictory, but it's in short summary, it assumes a plane wave under normal incidence. So you are actually measuring under a somewhat diffuse field, but assuming a plane wave at normal incidence, which is kind of contradictory, as I said, but it returns some practical results that you can plot and see the behavior of the material. And here is a comparison between that we did before between a reference ISO 354 and such method in the same reverberation room. So you can see that the measurements actually conform really well. And the fact is that the method is practical, but the model needs further explanation, in my opinion. This is also a measurement that a student made of a resonant panel, and there's a transfer matrix model as well. So you can see that it works well. It shows the behavior of the material, although we need to investigate this a bit further. And particularly, I think one nice question is, what is the surface impedance at diffuse field incidence, which is something that needs a better definition, maybe. And then coming into the array methods, this is part of my most recent work. What is the advantage? You can ask. I think in the previous talk, he said that we need practical methods, and I agree. This one is very practical, but what then is the advantage of using arrays? So this is part of a research project I started in 2020 in partnership with DTU, with Efren Fernandez Grande. The idea here is to use spatial information to decompose the sound field into plane waves. So you have not only two microphones or a single pressure velocity probe at a single point in the sound field, but we have a distributed array of sensors. This is an idea based on the past work of Tamura in 1990s, which was based on the spatial Fourier transform, but the spatial Fourier transform has a little bit of problems associated with periodicity and the need of the sample to be very, very large. The approach we take is based on what past work that has been conducted at DTU by Melanie Nolan and by Antoine, Richard, and Efren Fernandez Grande, and it's based on Fourier acoustics. So give a little idea. So we collect data from an array of microphones or receiver points. The array can have any format. I'm using here a double layer array, means that we have two planar arrays, two planes of arrays close to each other. From this measured data, we projected this measured data into a basis of L plane waves. And usually the number of plane waves that we have in our basis is much larger than the number of sensors that we have. And we have both propagating waves and evanescent waves. So this is what this figure here represents. This is the basis that we have of incident plane waves in blue and reflected plane waves in orange. And what is in the sphere is propagating plane waves, and what is beyond the sphere is evanescent plane waves. So we mount this dictionary of incident and reflected propagating and evanescent plane waves. And then we compute through a regularized solution the wave number spectrum, which we see a 2D plot here. Here in gray, you have the radiation circle. That means that everything that is inside the radiation circle is part of this sphere, orange here, and everything outside is part of the evanescent spectrum. What I mean by regularized solution is that the measured data, the pressure, is related to the matrix H that contains the incident and reflected sound fields, the plane wave basis, and each plane wave in the basis will have a complex amplitude. And this is the model, and the model, of course, the model considers noise and inconsistencies in this term. The propagating plane waves are the part that radiates to the far field, and the evanescent plane waves are the part that decay as the Z component goes higher. So this approach is based on what is proposed by the SONA algorithm, statistically optimized near field acoustical holography. So basically, what we do is to use a Tikhonov regularization to compute the amplitude of the plane waves. That means that we are doing this kind of optimization problem, which is open optimization. It's not constrained, but basically we're trying to minimize the difference between what the model predicts and the measured data. And while we try to keep the amplitude of the norm of the amplitude of all the plane waves under a limit. And this limit is calculated by this regularization parameter. And we compute an optimal regularization parameter based on the L-curve criterion. And once we have computed this X that is contains the information of the wave number spectrum, we can use it to reconstruct the pressure and particle velocity at the surface of the sample or any field point around the sample. And typically what we do is to reconstruct at a small grid on the surface of the sample and take an average at this small grid. So the array is much larger than this grid itself. So here I'll show some simulations. I know a bit past, but I have just a little bit of information to cover. We have a simulation of a finite absorber done with the boundary element method, and we can vary the sample size and the absorption characteristics of this sample. And we can also add Gaussian noise to each receiver in the array, so we simulate the addition of noise in the simulations. And what we see from the wave number spectrum is interesting because when we compute the wave number spectrum for finite absorbers, we observe these things here in the evanescent spectrum, which we do not observe when we simulate infinite absorbers. So this is the first thing that is interesting. When we have a finite absorber, we have this evanescent waves appearing in the wave number spectrum. This is associated to edge diffraction, as we see it, and in fact, the direction of the location of those evanescent waves are related to the location of the source relative to the absorber. So it is seemed really related to diffractions that happen on the frontier between the sample and the hard baffle around it. And another interesting thing, besides observing this phenomena in another domain, is that when we reconstruct the absorption of the sample, we retrieve consistently the absorption of an infinite absorber. So, for instance, here you have the infinite absorber, the prescribed in black, and we have a simulation of the infinite sample in gray, and then a simulation of several sample sizes in color. And we can see that the reconstruction is very similar, both for the high absorbent sample and for a low absorbent sample. And that is very encouraging because we have a method that can recover, even when we measure a finite absorber, which is always the case, we can recover very nicely the absorption of the infinite sample, which is, I think it's a good contribution. And it's harder to do it for low absorbent samples because we are measuring pressure and try to reconstruct pressure and particle velocity, and the reconstruction of particle velocity is trickier, especially when we have a low absorbent sample, because the particle velocity will be very small and the effects of noise tend to dominate in that case. So it's, although it is consistent through all the sample sizes, it doesn't recover perfectly the absorption in the low frequency spectrum because of the low value of the particle velocity. So that is about it. I have some just some quick conclusions, but I think we are past time, so we can skip it, and I can send the presentation later, so we can have this main important points. Rodolfo can pass it to you. So thank you very much for the invitation and for listening. Gracias. And thanks also to the partners at DTU Electro, particularly to Efran and colleagues there, and my colleagues here as well at the Federal University of Santa Maria.